introduce Aron Ahmadia for the second time in as many days. He's currently at Kaust, and he's going to talk about, as he was just alluding to, not solving the import problem apparently, but even though his talk says he's going to.
Yeah, I know. Well, Andy pressured me into this title, so I had to use it. Okay, so let me get my timer started. First of all, KAUST stands for King Abdullah University of Science and Technology. I'm a research scientist in Saudi Arabia. I've been there for the last 3 years. We have a scientific computing institute. We're actually doing a lot of stuff in computational science. We're Python friendly. We've been running Python tutorials and teaching classes with Python and even running Python on our supercomputer. So if you're interested in learning more about KAUST, come talk to me after the talk. So this is sort of the outline of what we're going to do. I'm going to talk a little bit about the problem. I'm going to talk about a few of the approaches that people have tried. So the idea is that you don't have to store or do the search for the imports every single time. You sort of cache your path of where things are and where they're hidden. You can load your bytecode collectively, and we'll talk about the difference between loading stuff through the file system and loading stuff through your collective networks. You can load your dynamic libraries collectively, and we'll talk about all of these different approaches. I'm going to give you just a snapshot of some experimental results. I'll tell you sort of my experiences with each of these things, but it turns out that a lot of this sort of ends up giving you the same results. And I'll talk about other things you would be surprised about seeing as affecting performance, and a lot of sort of my assumptions about what was causing problems and where the performance pains were wrong. And a lot of people have sort of come to the conclusion of what the performance problems are, and we'll hit them at the end. So this isn't going to be your classic talk of like somebody coming in and just kicking butt and just solving all these problems and hiding all of the details about what went wrong. I'm just going to tell you about all the things that went wrong for the last year. So hopefully this will be a useful talk for people, but it's not going to be a very exciting 103 kills, including the Energizer Bunny kind of talk. Sorry, this talk predates probably, or this slide predates half of the people in this room. It's Hot Shots Part 2. Okay, so let's talk about what we're doing. When we have a production code called PyClaw. We used to call it PetClaw, but the idea, Kyle's an author on this, but we solve really large hyperbolic systems of PDEs, and just loading PyClaw onto the full supercomputer, which is a mid-sized Blue Gene P, it's not even in the top 50 supercomputers anymore, took an incredible amount of time. Now, this was with the stock Python that was given to us by IBM. It was which was Python 2.6. It was with an older version of NumPy, and just upgrading to a newer Python, so a Python 2.7, and a newer NumPy took that from 4 hours to 2. So I can tell you that some of this is just legitimately a software problem, right? We're spending too much time importing, and we're making importing harder than it needs to be. So we can certainly, and I'm excited about Python 3 because they've cleaned up a lot of the import mechanisms. I expect that we'll be able to see performance improvements just coming from people working on Python, people working on NumPy. I mean, I follow NumPy dev now, and I've noticed that people care about import just even on a single computer, which is crazy to me. Like, why do you care about milliseconds? I care about hours. I mean, I'm wasting all sorts of things. We can just measure this in kilowatt hours, right? Yeah, it's like a small town there. We could measure this in CO2 emissions, and okay, this is not exactly green computing, right? We're wasting a couple tons of CO2. And of course, near and dear to my heart, we wasted 8 barrels of oil just loading Python and loading PyClaw on this big thing. Okay, so we had to do some sort of profile to figure out where this was going, right? So we have some resources. We hired some actors, and you know, just to give you a bit of a visualization, this is what's going on at the file system. You have 65,000 processes asking simultaneously for all of the metadata and all of the bytecode associated with your import. And it's a mess. See this poor guy trying to do something. He's got no chance. OK, so the problem is this. Your network file systems that we pay millions of dollars for on these supercomputers are designed only to handle a specific kind of problem. And that is all of the processes in this nice, orderly fashion say, oh, we're going to open this one file, and then we're going to write here, and we're going to write here. And nobody is trying to do anything like 65,000 processes simultaneously trying to get a lock on the .pyc file so they can all update it, right? That's just going to fall over. The other thing that really, really hurts these file systems is when all 65,000 processors are exploring the path looking for things to load. So when you say import numpy, Python doesn't immediately know where numpy is. So it has to traverse sys.path. And numpy may not be that first hit. And while it's traversing sys.path and it's creating all of the possible things that could give you a numpy module, those f-stats are racking up, and you're doing, let's say, thousands on a single process. If you have 65,000, you have millions of hits to the file system. And that just, it shuts down. It starts servicing things. And what I would call, I would say it looks like serialization, where you double the amount of processes asking the file system for something, and you double the amount of time that things are going to. So we saw this classic serialization where we had 65,000 processes. It took 4 hours, 32 processes, or 32,000 processes, 2 hours. So at some point, you just start paying that price. And we're trying to avoid that. We're trying to figure out how to make that not happen. And there are two things where Python is trying to get code in, right? It's trying to get bytecode in, right? These .py, .pyo, .pyc files. And these are just compiled Python source. And there's these extension modules. And I spent far too much time looking at extension modules. And that was a mistake. Because extension modules are actually a very, very small fraction of the file system activity for us. And that might not be true for you, right? So you should profile it, and you should measure it, and you find out how much time is being spent in the extension modules, how much time is being spent in the bytecode. We spend, let's say, on the order of now, let's say 5 to 10 minutes loading something on a mid-sized partition, say 10,000 processes. Of those 10 minutes, 10 seconds, 15 seconds will be spent in the extension modules. They're almost no time. OK, so bytecode. There are all sorts of solutions. PyFreeze is the first one that I looked at. And I Googled, because that's how I do research. I Googled, and I didn't see anybody really using PyFreeze. And I think people are using it, but people certainly don't talk about it very much. And so I'm going to turn this over to the audience at some point, because there are more experts in here than me, for sure. And I'd like to know who's using it and how much success they've had for things like really big installations, or lots of custom code, lots of numpy, lots of extension modules. If you just aggressively import everything, can you get PyFreeze to do the right thing? And can you get it to work in sort of a hairy, cross-compiled environment like a supercomputer? OK, zip import is cool. It doesn't work out of the box with numpy. If anybody has experience getting zip import working with numpy, please tell me. But as soon as I tried to combine any sort of basic magic of zip import with numpy and extension modules, the bytecode will work fine, but as soon as you try to find an extension module, whether it is or isn't in the path, or there's a similar numpy path, it just falls over because it can't find the extension modules that are supposed to be in the numpy package, but are not, because zip import by default doesn't handle extension modules. The other option would be to extend zip import so it can handle Unix extension modules. And I would have told you a year ago, oh, that's way too much work. And then I did way too much work on all these other problems. So maybe I should have started with zip import first. Path caching, I think, is the coolest approach. And that's because it's really simple. And it takes almost no effort to do. It's a couple hundred lines of Python. And you can just cache all of your paths right at the start. And this has a very nice effect. And then finally, the cool thing that we want to do is collective loading. And when I say collective anything, I mean use the very fast collective networks on the supercomputers. So we think of, I don't know what we think of as fast networks, but on Blue Gene and these similar capable computers like Cray, the networks are 10 to 100 times faster than your file systems. And they can be even faster for certain types of data movement and coordinated data access. So anytime you're in a situation where, oh, all 1,000 processes could ask the file system simultaneously for something, or one process could ask the file system for something and then give it to those other processes, if we can do it the second way, that's better. So collective loading is this other thing that we tried out. And so this is the other approach. How am I doing on time? 10 minutes. OK, we're halfway through. How's it going so far? Good. OK, at least I'm entertaining you guys. OK, so the first person who actually had a result in turning this thing on and speeding things up is this guy, Jussi from Finland. And he works on the GPOP project. So if you guys are familiar with Argonne National Labs, this is, I would say that these guys did a lot of the seminal work in high performance. Well, they did the Chicago seminal work in doing high performance computing with Python. And they have a paper in ICCS in 2011. And what they did was they took a Python, they took the Python source, they unpacked it, and they, everywhere that Python was doing I/O, said, oh, actually we're going to change this header so that you don't actually call fopen, you call our fopen and our fread and our fclose. And those fopens, fcloses, and freads all went through an MPI process that just did this basic thing of process 0 reads and then broadcasts to everybody. It's a little hairy, right? It's very, very, very intrusive. You've completely hacked Python, and you might be doing things that you don't want to do. And anytime any of the processes do something that the other processes aren't also doing, you basically break the code. So his performance numbers are really good, and these are basically as good as it gets. So that 4096, several people will take maybe half an hour if you're just using Python 2.6. Python 2.7 with a newer NumPy is not too bad. One of the problems here is I don't have an apples-to-apples comparison for you. GPA and Jussi's custom interpreter were not available to me, and so I don't have this. I only have the numbers he's reported. But everything here is kind of on the same level. We see that people do not get perfectly sort of log-n scaling. Your ideal situation is going from 2048 to 4096. Well, that number is funny, right? Because you don't see this performance knock going to 4096. But if we took it just a little bit further, you would see that double again. So he's sort of, this is this fortuitous thing. And I'm not sure what's causing it. We see something very similar in our file system. But going from 512 to 2048, 4 times as many processes, we would hope to see just a very small bump in the time. But since it's looking like some sort of sublinear scaling, we're getting bad performance. And we keep going up to larger and larger number of processes, right? The new Lawrence Livermore machine has 1.5 million cores. This is not going to work on 1.5 million cores. It's just going to fall over. So the other approach that we work on is this sort of extension modules and how to deal with these. And we totally solve this problem. So Jed Brown and I worked on this. I think there was a small report on it last year. And we've shown that you can go into glibc, you can touch just the pieces of the runtime dynamic loader that do dlopen, dlsim, dlclose. You can intercept those, and if you're just doing dynamic libraries or any sort of extension modules, we can do that extremely fast. Jed has a result on Blue Gene Q where he imports C-types, which is just an extension module, and he can do that in milliseconds on thousands of nodes. So we've solved that problem, and we've ported it to tons of environments. If you have a glibc, we did it on 2.4, 2.12, 2.14. It's not hard. There's only a few different places to touch. That said, it's not hard now. It took me forever to understand glibc. So going in, the other person who's done some work is Asher Langton, and his approach is just this path caching that I was talking about. He originally didn't know about PEP 302, and I think he went to PyData. There was some conference this year he went to, presented his results. They said, oh, use PEP 302. So he rewrote it using sysmetapath hooks, and that's very nice. And he doesn't do anything collectively. All he does is just modify sysmetapath with his own collective or his own cached importers, and those just go into the file system, check to see where all the paths are once, and then avoids doing that crazy probing every single time you try to do a normal import. Okay, so the other way that we could do this is with this collective bytecode probing and loading. And that, instead of just caching the file system paths, you do everything collectively, right? So this process, we want to do an fstat, and so all the processes wait on process 0 to do the fstat. Process 0 does the fstat, it comes back, and then broadcasts the results to the other processes. And wsculin, this is Walla, is the name of this project, and he's been working on it for about 2 years. I recently picked it up over the last couple of months, and I've hacked on it and got something working with sysmetapath as well. Like I said, this third approach is this work with JED, and these are the POSIX calls that we needed to intercept. So there's, I think, I skipped munmap in there, but there were 6 functions we had to re-implement completely down at the glibc level. Once those are implemented, you can actually use collective file system for anything. So we use it to do dynamic library interception, but if you wanted to use it just for very, very basic collective file system stuff, you could hook MPI-IO on the back end of it. But for now, you can use it to intercept any sort of open, close, read, seek, call in a code. So if you have Fortran code that's 30 years old, and let's say it's even compiled already, but it was compiled with support for static libraries, you could actually use this to intercept that Fortran code and intercept all of its file I/O. And all of this stuff that I'm talking about that has my name on it is available on GitHub. So this was our experience working with glibc. I strongly recommend against diving into there unless you really have sort of a high threshold for pain. Sort of these are the final results coming up. And like I said, we didn't really solve the problem. So this is Asher's results that I'm showing on the right. This is his cached import being used on our system, which is PyClaw. And so 16,384 cores, that's a quarter of the machine. That's being loaded in a little bit more than 5 minutes. So we can do the entire machine in about 20 minutes, which is an improvement. This is the worst factor of 10 speed up I've ever reported in my life. And it's just because it feels very unsatisfying to see these numbers up here and to see these loads and knowing that if we double that, it's going to double again when it shouldn't be. So there's an unsolved problem in here, and I don't know what it is. Right? It's really, really hard to go onto the machine and say, tell me every single time you're hitting the file system. You need like a special person who knows just how to do that to do it for you. Right? And then you need to understand what's going on in glibc. You need to understand the interaction between Python and the C profiling. So it was all really, really hard. And so I am standing here and admitting defeat on the import problem. But I'll say that Asher's approach is simple. It's dead simple. And unless you're doing something really complicated, you should just use it. I've timed it, and it's extremely simple to use. I use the MPI for Pi finder. He recommends, I think, something called the Simple Finder, which is also a similar approach, but doesn't broadcast all of the caches. I think all of the processes do their caching immediately. You'll notice that there's a little bit of startup time on it. So there's this 18 to 29 seconds, and then it just sort of blows up while doubling out here. But that startup, that higher price for startup comes from traversing all of the paths in sys.path in the beginning. So that's sort of this immediate upfront cost that you pay, and then everything sort of goes from there. OK, so here are our conclusions. We haven't solved the problem. We've done some improvements. There are a lot of places to get stuck. Focus on the bytecode and focus on the paths. That's where you're going to see that your best improvements. Don't worry about the extension modules. It's a cool thing to do, and we have a solution if you're interested in it. But actually throwing our code in, our extension modules on, slows this down on the cached import. So I have a version of the code that works with bytecode loading, that does the cached import, and does the extension modules all in one whole enchilada. And it's actually slower. And the reason why is it because it synchronizes the processes on every single time step of everything it's doing. And it turns out that's slower than just letting the cached import hit things as needed. You can imagine that the serialization hurts you in this case, or the synchronization hurts you in this case. OK, so I'll turn it over to you guys. I have opinions, or I want your opinions. Yes?
Yes, Andrew Usselton. I'm with Lawrence Berkeley Lab. We have a couple of big crays.
Yes.
We hit this on a regular basis. I'm actually the file system guy. I do monitoring on the file system. I don't know how easily you guys can see this. This is the metadata server.
Yeah.
24 hours worth of data. The black line there is the CPU utilization. The top of the screen would be 100% CPU utilization. We've got our metadata server is maxed out all day. This is Python.
Yeah.
Lester? Yes, Lester. Crazy.
I mean, I'd be happy to come over and talk about what you guys are working on and how to use it.
We're actually looking. This is actually from back in November.
Yeah.
There are some people who've been working on it.
Yeah, I didn't mention that I had a paper. There was a paper I think from Sandia at a Cray users group, but I couldn't read the data, so I didn't include it in my
I will
talk.
hook you up with the gang who are looking at this. I'm just the person who's like the witness. I do the data monitoring of the file system, and I go, yep, there it goes again. I don't claim to have lots of solutions. Although what you listed there, that's exactly the things they're working on as well.
Okay.
So can we get the next speaker to come up?
Yeah, but please give me feedback and things that you guys have done that solved problems that were similar. Yeah.
So in the past, we've used, actually from the GPOP project, they had instructions
Yeah, go ahead.
on how to compile a monolithic Python interpreter that included all the extension modules. Do you see a reason why doing that in combination with, say, zip import and broadcasting the zip processors wouldn't work?
I don't think it would work. I think that they mentioned that they can't do it with NumPy, right? So if you have normal extension modules that are completely independent, I mean, this is a NumPy question, right? Can we, or maybe it's a zip import question. Can we modify zip import or something in that path caching so that if we have extension modules that live in NumPy, can we hide them out? I think it can be done. I mean, I know it can be done. But we didn't try that path. It's a great thing to try. You might get results in a week.
Just not to be the Python too much, but I work at a super data center. That's the #1 problem for everybody. Is getting the file system too much. If you get that fixed, then you're golden. Most people don't. So
Okay.
it's not only our problem.
Yeah.
Okay.
Cool. Well, thank you for your time and your attention.
Let's give Aaron a hand.